Hello everyone, I'm Kiho. Today I'm going to talk about the linear representation hypothesis in the geometry of large language models. This is joint work with Yeo-jung and my advisor, Victor. In the context of language models, the linear representation hypothesis is the idea that high-level concepts are represented linearly as directions in the representation space of a model. So, what does linear representation actually mean? There are three natural ways to define the notion of linear representation. The first idea is the classic word 2-vec subspace notion, where in the representation space, woman minus man, queen minus king, and the differences of all similar pairs belong to a common one-dimensional subspace. It is natural to take this subspace to be a representation of the concept. The next idea is the linear prob notion, where we can measure the probability of a concept value using logistic regression. In this case, we can take this coefficient of logistic regression to be a representation of the concept. The final idea is the steering vector notion. We can change a concept of the context by adding a suitable vector to its representation without changing any other concept. We can take this added vector to be a representation of the concept. The problem is that it is not clear how these ideas relate to each other, nor which is the right notion of linear representation. Our strategy to address these challenges is as follows. First, since the definition of high-level concepts is also not clear, we formalize the notion of a concept. Then, we formalize the subspace notion of linear representation. And then we use softmax structure to connect them to measurement and intervention. Before defining a concept, we require some background on large language models. At each step, LLMs take context as an input and output the next single word. They first map each context x to a vector lambda x in a representation space. We call it an embedding vector in the embedding space. LLMs also represent each word y in the vocabulary as a vector gamma y in a separate representation space. We call it an unembedding vector in the unembedding space. Then the probability distribution over the next words is given by the softmax distribution of the dot product between lambda x and gamma y. Now we formalize the notion of a concept. We take a concept variable w to be a latent variable that is caused by the context x and acts as a cause of the output y. For simplicity, we restrict attention to binary concepts with ordering. So formally, a concept variable w is defined by a set of counterfactual outputs that differ only in the value of w. For example, the concept male to female is defined by pairs like man-woman and king-queen. Here, we especially state that concepts w and z are causally separable if y, w, z is well defined for each value of w and z. This means that the causally separable concepts are those that can be varied freely and in isolation. For example, gender and language are causally separable. You can consider the word quadruple, king, queen, hua, and hil. Now we formalize the subspace notion of linear representation in each of the unembedding and embedding spaces, since a concept could be linearly encoded in either space. So in the unembedding space for the next word, we say that a vector gamma bar w is an unembedding representation of concept w if the differences of any counterfactual pairs like queen minus king are parallel to gamma bar w. Similarly, in the embedding space for the context, we say that a vector lambda bar w is an embedding representation of concept w if the differences of any counterfactual pairs like she is the minus he is the are parallel to lambda bar w. Then, using the softmax structure, we connect them to measurement and intervention. First, we prove that the unembedding representation gamma by W is also a predictor for the concept W that is linear on the logic scale, like the linear representation learned by feeding a linear probe. Also, we prove that adding the embedding representation lambda by W to the context embedding lambda can change the probability of the target concept W, but not those of off-target concepts, which are causally separable with W. So we have formalized the linear representation hypothesis, but two other natural questions follow. How do the unembedding and embedding representations relate? Since the subspace notions are defined in each space, we want to know the connection between them. And what is the right inner product for the representation space? When we have linear representations of various concepts, we can hope to use the cosine similarity or orthogonality for interpretation and control. However, there is no natural inner product for such geometric notions, since multiplying an invertible matrix A like this preserves the softmax distribution, but changes the inner product within each space. So we want to find an inner product that respects the semantic structure of a language. The idea of causal inner product provides the answer to these questions. We define the causal inner product as one where the unembedded representations of causally separable concepts are orthogonal. Then, we show that this causal inner product has the special property that it unifies the unembedding and embedding representations via this correspondence. This figure illustrates that the geometry of linear representations can be understood in terms of a causal inner product. On the right, we show how the mapping induced by the causal inner product transform the representations. Gamma maps to G, while lambda maps to L. The key takeaway is that the unembedding and embedding representations, red and blue on the left, are unified as the same representation in purple on the right. Moreover, we give a simple scheme for estimating the causal inner product. The one that we use involves the invariance of covariance gamma. With this in hand, we can measure the similarity of concepts by using cosine distance. Experiments with lambda-2 representations provide evidence for all aspects of our theory. First of all, we validate the existence of linear representation. We estimate the unembedded representation gamma by W for various concepts by using the counterfactual pairs from a word analogy dataset. Then we project the differences between the unembedding vector of counterfactual pairs onto gamma by W. For example, we project Paris minus France onto the unembedded representation for the concept country to capital. They are compared with the projection of random pairs, and this histogram shows that the differences between counterfactual pairs are clearly more parallel to the unembedded representation. It supports the subspace notion of linear representation hypothesis. And next, we check if the invariance of covariance gamma provides a causal inner product. This heat map shows that the estimated causal inner product between the unembedded representations of causally separable concepts are close to zero, which means that they are approximately orthogonal. For example, the dark blue blocks for causally separable concepts such as male to female and English to French indicates that their unembedded representations are orthogonal. On the other hand, the bright blocks for some correlated concepts, English to French and French to Spanish, indicates that their unembedded representations are not orthogonal. Next, we show empirically that the unembedded representation is a linear prob on context. The left histogram illustrates the embeddings of the random context from French and Spanish Wikipedia are separated by projecting onto the unembedded representation for the concept French to Spanish. On the other hand, if we use different concepts such as male to female, the unembedded representation does not act as a linear prob. Lastly, we want to control the concept of the context. Using the estimated causal inner product, we can obtain the embedded representation from the unembedded representation. Here, for three mutually causally separable concepts such as gender, capitalization, and language, we look at the changes in logits by adding each embedded representation to their context embeddings. For example, adding the embedding representation for the concept male to female to the embedding of the context long-lived changes the logits between queen and king, but not that between capitalized king and lowercase king. Therefore, this shows that the embedding representation can be used to control the target concept while keeping other causally separable concepts constant. In summary, we formalize several notions of linear representation and show their interrelations. Then, we show that every notion of linear representation unifies with the right choice of the inner product. If you want more details, please visit our poster and this archive link. Thank you.